Okay, the last part of the intermolecular force chapter that we have to take a look at then is the chemistry of water. Okay, now what's very, very, very important to remember is that the shape and the type of intermolecular force that holds water together actually gives it its properties. Okay, and probably one of the most important things, and something that I can advise you that you need to be able to do, is you need to go and you need to draw the diagram to prove why water is a polar molecule. So we know that it's a hydrogen atom with one valence electron bonded to an oxygen atom that's got 6 valence electrons, and then it's bonded to another hydrogen atom. And then you can remember from the previous chapter that these ones here is what we see as our bonded atoms, okay, and these ones here are our lone pairs, in other words electrons that only belong to the oxygen, and lone pairs don't like bonding pairs. That's why the lone pairs will rather be grouped together and the bonding pairs will rather be grouped together. That gives water that bent or angular shape. Then we also know that when we take a look at the hydrogen, it's got an electronegativity of 2.1. Oxygen has got an electronegativity of 3.5. That means that the shared electrons will rather spend their time around the oxygen than around the hydrogen because of the higher electronegativity of the oxygen. That means that the oxygen side of the molecule is slightly negative, and that the hydrogen side of the molecule is slightly positive, making this a polar molecule. But then also we have a hydrogen bonded to a highly electronegative oxygen atom, meaning it's following that Knopf syndrome for hydrogen bonding, and we know that it will make use of hydrogen bonds to bond its molecules, being our strongest intermolecular force. Okay, so if we take a look then at the water molecule and a couple of its properties, there's about 55.5 moles of water in 1 liter of water. Now this is equivalent to 3.34 times 10 to the power of 25 molecules of water. Now that's a massive amount of water in a very small volume. Okay, the water molecule is incredibly small, and because it's incredibly small and polar, it can surround anything that's dissolved in it, which makes it a wonderful universal solvent. Okay, then like we said, it makes use of hydrogen bonds, the strongest type of intermolecular force. So the oxygens on the one hydrogen on the one water molecule will be attracted to the hydrogen on the opposite water molecule, and so on and so on, which allows it to form very, very strong bonds. Now, what are the unique properties of water? Okay, so just interesting fact there for you. Antarctica has one of the world's largest freshwater lakes. It's 4 kilometers below the snow. It's 200 kilometers long and 50 kilometers wide. Okay, this is one of those glacial lakes that, well, most of them don't ever see the light of day, but even at that depth, the water is still in a liquid form. So the 5 properties that you need to know, and this can be a long question. Okay, so if you ever get a long question, and it won't be name the 5 properties, it'll be like the polar ice caps are melting due to global warming. Explain why using the properties of water, why this is not a good thing, and then you will have to name these different ones and apply them to that problem. So the first one, specific heat. Specific heat is the amount of energy that is needed to increase the temperature of a unit mass of a substance by 1 degree. Okay, water has a high specific heat. That means it has to absorb a lot of energy before its temperature will be a degree warmer. Okay, absorption of infrared radiation. Water is able to absorb a lot of infrared radiation, and the ocean and other water bodies are heat reservoirs that help moderate the Earth's climate. Now, because of that very high specific heat and the absorption of infrared radiation, and the fact that 70% of the surface of the planet is water, the water absorbs a lot of the infrared radiation from the sun and stores it, and that helps our Earth have very, very narrow daytime and nighttime temperatures. Okay, other planets in our solar system go from 100 plus degrees during the day and minus 100 degrees during the night, where we don't have those fluctuations, because during the day the water absorbs the energy, and then during nighttime, when the air surrounding the water gets cooler, the heat flows from the water back into the air, moderating the actual nighttime temperature. Okay, then boiling and melting point. Water has a very, very, very low melting point and a very high boiling point at 1 atmosphere. Okay, 1 atmosphere just means the atmospheric pressure that we are feeling right now. Now this means that water exists as a liquid over a very, very, very large range of temperatures, which is one of the unique things about water, because Earth isn't the only place we find water, but Earth is the only place that we know of that has liquid water, which is an essential building block for life. Then high heat of vaporization. So the heat of vaporization is the energy needed to change a given quantity of a substance into a gas. For water, it is 40.65 kilojoules of energy per mole of water. That means the water has to absorb a massive amount of energy before it vaporizes, before it turns into a gas. And then probably one of the most important ones, the less dense solid phase. As water solidifies, the hydrogen bonds between the molecules expand. So basically what happens is that as the water molecules freeze, the hydrogen bonds become more rigid, more unflexible. They move a little bit further away from each other. They're still bonded, but that makes ice, solid ice, more dense than, less dense than water, meaning ice floats on water. Now this is incredibly important for our planet, because if it gets very, very cold and the water freezes and it's sunk down to the bottom, then the top layer would just freeze again and sink, and so on and so on and so on, until the entire ocean or dam or whatever we're looking at is frozen solid. But in this case, because the solid phase is less dense, when it freezes, it creates an insulating barrier over that water body, protecting the actual aquatic life underneath it, and therefore limiting the actual fluctuations in the temperature. Okay. That is then our intermolecular force chapter. Thank you.